right, good afternoon. For those of you who do not know me, my name is Ali Kujuri. I'm an adjunct professor at the Engineering Science Department and one of the organizers of this lecture series. I should thank Mr. Sharam Mariwani and also Kate Lab who helped me organizing this lecture series. On behalf of the department and the School of Science and Technology, let me thank you all for coming to this 7th lecture this academic year and 130th, believe it or not, a lecture since we started in 2006. All right. Before I introduce our guest speaker for today, let me mention that first at 5:30, Kate has ordered pizza. It's by the way delicious. You like it, okay? Which is going to arrive at 5:30 right after the lecture. And then for next, on February the 15th, we are going to have another interesting talk titled How Technology Helps Save the World's Most Valuable Resource by Mr. Peter Carson, and he's the Chief Technical Officer at Hydropoint Data Systems in Petaluma. In fact, both Enphase and then Hydropoint are in Petaluma. I think we are very close to each other, right?
Yeah, we're on kind of the north end of Petaluma, North McDowell Boulevard. And by the Applebee's, if you know where that is.
Yeah. They're in the same place, by the way. In the
oh,
park.
are they? Because
yeah,
they used to be on the other side. I guess they've moved. Huh?
Well, I don't know. I don't know where, but they should be close to you.
Okay, you bet.
So anyhow, our guest speaker for today is Mr. Mark Baldassari, and the title of his talk is, as you can see, Photovoltaic Microinverter Systems. He has 34 years experience in engineering and product development and over 10 years with Enphase Energy, where he holds the position of Director of Codes and Standards. Currently, he actively participates in a number of codes and standards development groups, both domestically and internationally. Domestically, Mr. Baldassari regularly participates in IEEE 1547 series of standards development with emphasis toward improving the grid integration of photovoltaic systems, and he's involved with Underwriters Laboratory working on the harmonization of UL, International Electrotechnical Commissions, that's the IEC, standards and standards technical panel members of UL 1699B and UL 2703. Mr. Baldassari is an active member of the CAL SEIA codes and standards and PV industry forum. He's very involved with the drafting of the 2020 National Electric Code, that's the NEC, for Articles 690 and 705 as chairman. Mr. Baldassari has a bachelor's degree in electrical and electronic engineering from California State University in Sacramento. This is in fact the second time that he is here as a guest speaker, and the reason that in fact I invited him again are two reasons. First of all, you as an engineer who are going to graduate very soon, you really need to understand what the photovoltaic is and then how it's converted to AC. I mean, you need to know that. Probably some of you will install it in your house quickly. And also the fact that he's a very good speaker. His talk is very interesting and instructive for all of you. In fact, he was gracious to give us tours to his company twice so far. And right before I came here to school now this afternoon, he in fact offered that he can give us another tour for you guys. And I'm really thankful to him. So the tours that in fact we have had so far, you can ask your colleagues, have been really so instructive because they learned a lot. What you learn is that you'll see about, of course, the panels and so forth, and then how the inverter works. What's different between inverter and microinverters, because that's what they are doing. They build battery. You want to see now how the batteries work, especially for when you want to use it with the inverters. And the equipment required for testing, temperature and humidity variation, voltage surges, and durability and interoperability. All of these things are really big thing for engineering. So, when we are talking about standards, that means interoperability. That is how the systems from different companies can connect to each other and so forth, all right? And then also as far as the temperature, remember now, the inverters that they are using is going to tell you that you can use it in Phoenix, Arizona or in Alaska somewhere, all right? So let's just give him applause.
Okay. Well, thank you everyone for giving me an opportunity to address you guys. Yeah, Ali was talking about the testing, and if you come to the tour, that's one of the big themes that you'll see is testing the product, because as engineers, when you design something, you draw a schematic, you simulate it, you do all that work, you build it, and then you turn it on, and you have to assume it's broken. Even if it looks like it's giving you the right voltage and current and everything, it's still broken. You got to test it. You got to continue to test it. You got to put it in the environment that it's going to be in, temperature, humidity, those kinds of things, and you have to set the voltages too high and too low, and the frequency high and low, and you have to really beat on it to make sure that your product really works or your design really works. But if it looks like everything's working, you haven't tested it enough, because you got to test it till it breaks too, and then you got to figure out why did it break and how do I make it better so it doesn't break. So anyways, if you come to the tour, you'll get a lot of that. I'll show you how we go through all the steps, and you'd be amazed. Everything, it's always being tested. We never stop testing it. It's amazing what you find out when you test something. So anyways, thanks everyone for letting me be here again. My name is Mark Baldassari from Enphase Energy. I'm the Director of Codes and Standards. Ali read off a bunch of the standards work that I do. Sometimes standards can get pretty dry and boring, but it's sort of like flying a plane. It's hours of boredom punctuated with moments of excitement. There's usually something pretty cool that happens within a standard, or we look at it. My role at Enphase and with the standards group is I'm kind of like blocking and tackling ahead of the runners. I want to make sure that we have the field where we can, we can get our product out there. We want to make sure, and we can also do strategical changes to a standard or a code that we're aligned with, but maybe our competitors are not. So that's kind of the stuff that we do. There's a little bit of strategy going, some offense and defense at the same time. But there's a great group of people that work in that industry on the codes and standards side, and I've been doing it for about the last 5 years, but prior to that, a lot of design work, mostly analog design, transistors, resistors, capacitors, the simple things. But then, today everything's in an integrated circuit and so forth, but when you get those signals in and out of that integrated circuit, it's back to analog again, so that's always a good field to look at. Today I want to go over some of the photovoltaic microinverter systems that should say up there. We changed the title for this year, and in here today we're gonna go over some of the basics of a photovoltaic module. How we get power out of this thing. How they're built up. What's inside one of these things. Then we're going to look at some simple systems, and then I want to talk about storage, energy storage. That's a real big up-and-coming field. You've heard a lot about it. There's, Tesla Powerwall. There's the Enphase, what we call AC battery. ABB power systems, Siemens, Schneider Electric. All these companies have storage systems, plus hundreds more. So, and that's a real big up-and-coming field, and so I'll show you a little bit about that. And then if we have some time, I know Ali wanted me to kind of go over some of the basics of what an inverter is, and I've got a schematic here, and we can draw some pictures on the board, so hopefully we can get into that too. So here we go. So this is a map here of the world, as you can recognize. And it's coded here for different amounts of solar radiation. So obviously the more red, that means you have more hours of sun during the day. And then up in the north, you can see some of the colors are straying over to green. But I want to point out Germany over here. Look at the color of this thing. It's fairly green, yellow. That kind of equates to the same kind of sunlight you see up in the Northern Territory of Canada. And Germany has got probably the highest or the most amount of PV, and they have for many, many years. They've really developed and have installed more and more of that. And look, it's not even a very rich area for sun. It still makes sense. I mean, a lot of people say, oh, geez, there's not enough sun. There's not enough sun in San Francisco. But believe me, San Francisco has more sunlight, more hours of daylight than what the whole country of Germany has. So it makes sense everywhere. That's what I'm trying to get at. And we do have installations that are all over the globe. In fact, we do have some down in Antarctica, which is really quite interesting because there you have some parts of the year where you're in total sunlight. And they actually they have a shack that had PV modules on all sides because during the summer months, the sun actually rotates around it, and even a module on the roof. So you can even do some stuff out there. You don't have to have some ideal Arizona sun or something like that to make PV work. So the basic element of a cell, it's a PN junction. And when the photons of light hit the silicon cell, then it dislodges an electron, and then we get a power flow. So that's how it's doing it. It's a totally passive object. It doesn't require any stimulus except for photons. It doesn't require any kind of moving parts, and it's very simple to make. Typically, the front and back have conductive wires, I guess you could call it, contacts, electrical contacts. And if you look at a PV module and you look at the cell, you'll see little stripes of wires that go across it, and that's to collect the free electrons that then can flow through the circuit. The other thing are the terms. I'm going to be calling these things solar modules, not solar panels, because the real correct term is a solar module. The press calls them a panel. People call them, hey, I got solar panels on my roof. Well, solar panels are really, those are solar thermal in nature. At least that's the correct definition. So solar panels heat water, solar modules generate electricity. Sort of like we have windmills and wind turbines. Windmills grind up grain, and wind turbines generate electricity. So those are the proper terms. So anyways, a solar module is a collection of solar cells. When I have modules together, then I can call that a panel. And then when I take these panels and arrange them in an area, then it's called an array. So those are how you would look at it. So you might say, well, on my roof I have one solar panel made out of multiple solar modules. I guess you could say that. That'd be the proper terminology. So the other characteristic is what we call the IV curve. So we have current going up here on the y-axis. We have voltage on the x-axis. This kind of orangish line here is the operating characteristic of the solar module, or it could be a solar cell. We don't have any magnitudes out here, but this is the shape that it has. So we have constant light that's hitting it, and if you were to look at the voltage across it, you'd see that it would have this transfer characteristic for current. So where is the maximum power point for this module? Well, it'd be wherever you get the highest current and the highest voltage. It happens to be about right here. If I go down on this curve this way, well, my current is going up, but my voltage is going down. So the product of course, current and voltage is power, and that happens to cross over right here. This blue curve is a mapping of the power output of the module. Here we got power on this secondary y-axis. So as the voltage goes up, you get to a peak power, and then it falls off again. So we call this point the maximum power point. This is critical for PV systems. This is where you want to operate. I want to operate at the maximum power point. I want to extract as much power out as I can. I want to get the maximum harvest, is another term we use, of energy from this solar module. So I need to find this maximum power point. What's interesting, in the inverter, and over the years, everyone has their own algorithm for finding and tracking that maximum power point. As light conditions change, this curve will change in shape, and temperature will change the shape, and we'll take a look at that. But the inverter has to find that maximum power point. And if the algorithm isn't working right, you might slide back on this curve somewhere else. Or if you want to output less power, what we call curtailment, then you want to slide down this curve over here. Now here I'd be at less power down at this point. So there's some reasons, this curve gives you the maximum power point, but you also use it to regulate how much energy, how much power you're pushing back, say, onto the grid. So this is what the curves looks like with various degrees of irradiance or sunlight. Here we have kind of the standard value for irradiance is 1,000 watts per meter squared. That's kind of sea level, 25 degrees C, not a lot of humidity. I don't know the exact conditions, but it's like that. So if you got a nice sunny day, the sun is up high, you're going to get 1,000 watts of energy for every meter squared. That's pretty good. So we got a lot. That's why you can see that the sun is putting a lot of energy onto this planet every second. And so there's a lot that can be captured and converted into electricity. As the irradiance goes down to 800 watts per meter squared, or down to 200, notice how the curve changes, and then the maximum power point is also shifting accordingly. So that's one thing that the PowerPoint tracker has to do. It has to find that maximum power point as conditions change. So that's one degree of freedom here, is the amount of light. The other one is temperature. Temperature can work and hurt you, work for you and can work against you. So here's kind of the nominal curve, 25 degrees C. But if the weather is colder, look what happens to the voltage. You get more voltage out of more open circuit voltage out of the module. So you actually get this power curve is moving over. Now, at almost the same current I was at 25 degrees C, I now have more voltage. So I get more power out of this thing. So colder modules put up more power. Hotter modules, the maximum power point slides back. So the best conditions are lots of sun and cold weather. Denver, Colorado. You got high altitude, the air is thinner, temperatures are colder. So you get the irradiance is actually higher in Colorado than they are in San Francisco, just because of the amount of atmosphere. So in San Francisco, maybe you're at 1,000 watts per meter. In Colorado, you'll get maybe 1,200 watts per meter squared. The other thing that's interesting is there are also other ways that affect power are reflections off of clouds or snow. That's where if you have sunlight coming down onto a module and there's a white puffy cloud, sunlight is also hitting that cloud and bouncing onto the module. So you get a boost, you'll get more radiation onto the PV module and your power will go up. And it's really interesting with the N-phase system, you can actually see where you have what we call cloud enhancement. So on days that are kind of cloudy, you can see where the energy output actually peaks up above average because it's got cloud enhancement. Kind of cool effect. So now that we know how a cell and a module work, and panels and all that, now it's put together with a system. This is what we tie into an inverter. So what is an inverter? Well, you guys are familiar with inverters. You've heard of that before. I mean, they have inverters in cars that you plug into the cigarette lighter and adapter, and you've got AC power. An inverter takes a DC power and converts it to AC power. And with photovoltaics, you have what comes out of the PV module or the PV array is DC current. which is not as, yeah, it could be useful within our house. Today, not so much. We have 120 volt outlets. We want to be able to plug in, so we convert the DC power to AC power, and then we connect that into the, say, a house. I'll use a house as an example. Of course, that applies to three-phase commercial systems or transmission systems for utility scale, whatever. But you know, they all use the same basic principles. This is how a string inverter works. So this is traditionally, a string inverter is the traditional architecture for PV systems. And when I mean string, what I'm talking about is that I have these solar modules and they're connected in series to each other, and then they're connected over to the power inverter.
Yeah, it said if one you can use
the green one, think will be brighter?
Yeah, they can see here.
Okay. Yeah, oh wow, nice. So these are in series. So we all know series connections. Each one of these is putting out a voltage, as we saw in the previous curve, and then we're going to add that to the next module, which is putting out a voltage in the next. So here we're going to add the voltages up in series, and then we're going to have a much higher voltage out here at the end. And it says our traditional systems are running up to 600 volts DC. And so you have a lot of voltage. They're in series, so we're not adding currents. The current of one is passed through to the other. And here we have a very high voltage, and the current of one of those modules is then connected in series. Or you know, you can't make it any greater than the lowest current, which is kind of a problem. One of the issues is that we saw with irradiance to power point changes, and if we go back to those irradiance curves, with irradiance, look at the current is really changing a lot. This must be one cell looking at these values here. Not a module, it's a module, but it's a very old module, low power module. So look at the current. We're at 3 amps here with all the sunlight, but if I have a lot of shadow, look what happens. I'm down here to a ½ amp. Okay? So in a series configuration, one of the drawbacks is that if one of these is shaded, it's going to limit the current for all of them. So it's sort of like, I use the analogy of a garden hose. And the garden hose is laying on the ground and water is flowing through it. And wherever I step on that garden hose, I'm going to limit the amount of water that flows through there. And that's exactly what happens with a string inverter system, a string system. If one of these is shaded, it's going to limit the current through the entire thing. So if I'm at a ½ amp here at 600 volts, I've really dropped my power. You know, really dropped it a lot. So this is one of the advantages of, also you get this high voltage DC, which can be very dangerous. Let me jump ahead. This is a microinverter system, okay? So a microinverter why do we call it a microinverter? Well, first of all, it's small. I should have brought one. A microinverter is about this big. You know, it's a little bit bigger than my Galaxy S8 Plus. It's a little bit bigger than a Note 8. It's small. It's micro in size, if you will. And each one of the modules here has a microinverter attached to it. So and all of these are now connected not in series but in parallel. So here, if I have shadow on one of these, it will put out less power. It will put out less current. But all the rest of these, which could be in full sunlight, are still going to be putting out their maximum current. And so now, if one of these is shaded, you've only lost the output of one of these modules. It doesn't affect the whole string. The other thing is, the other analogy I like to use are like Christmas light bulbs. So with the string inverter, everything's in series, and those are like the Christmas light bulbs that you got on your tree, most likely. You unplug one, and all of them go out on that string. But with the microinverter being in parallel, it's sort of like the old-fashioned light bulbs, where you unscrew one, it turns off, but the rest of the light bulbs are still on. So that's how this is different in architecture. But it comes with its own set of problems. if we go back to the string inverter, I have one inverter that's located on the house. And with the microinverters, well, you've got lots of them. Well, that's kind of good and bad, actually, because if one of these goes bad, the rest are still running. But if I lose my string inverter, I've lost it all. If that fails, everything's down. You get nothing. At least with this system, it has some resiliency. There's through redundancy that really helps out with the overall output. So when you start thinking about, well, to a house, maybe it doesn't make a whole lot of difference. But if you look at utility scale, where you're getting up to very, very, very large inverters, one loss of a string inverter, and you might lose a megawatt of power. I mean, whoever's running that plant's gonna be on the phone right away, trying to get some technician out there to fix that thing in a hurry. And because I'm losing so much energy, but with microinverters in a large scale situation, like a megawatt scale, you'd have, I don't know, 5,000 inverters. If one goes bad, well, you can schedule maintenance to come in and take care of it later.
Excuse me.
No big deal. Yes, sir.
Could you put the solar modules still in parallel and with one inverter at the end?
With the string situation?
But the string, they were in series.
Yeah.
This is in parallel. It's lower voltage.
Yeah.
But with one.
Yeah, this one, we're converting everything to AC at this point.
Oh, I see.
So there you have your DC on one side, and then this is AC. So now we went ahead and converted that to AC, and are adding that up into the AC side. You get into trying to parallel PV modules runs into problems again, because they're not exactly matched, and you're going to have one fighting the other, and you'll have current. If one is putting out less voltage, then the other one will then feed current through it, and other things, and they just don't work. They don't work well in parallel like that. It's like paralleling batteries. The only way you can do that is by putting some kind of impedance between them to equalize them. Or you're trying to parallel transistors. One's going to hog the current, the other one's going to kind of relax a little bit. So you need some way of equalizing it. So the simple thing to do is hook them up in series, or here they are, they're in parallel, but we have electronics between them buffering each one of them.
Can't you just use diodes when parallel?
You could. And then you have the loss of the diode that you can, of course, you can shot keys. A typical module is, the modules today, they're, the kind of the high wattage modules are about 330 watts. The low ones are in the 250, 280 range. So you're running probably 8 amps to, 8, 9, 10 amps. Even a shot key is going to give you a fair amount of power loss. So you got to kind of weigh that in. Do you want to put, if we figure, I don't know, a shot key 0.3 volt at 10 amps, look at 3 watts on each one. And do you need one in the positive and negative leg? So there's a lot of wasted power. But it's possible. It's possible. You could do that. If you don't, if you got some extra power to burn, that would be another way of doing it. Just showing some of the voltages around the system. Let's just go past some of these. So this is I probably should have shown this slide first. These are the microinverters underneath a PV module. So we're looking underneath. We have the racking running here. Here's a person kind of stooped over. We have the DC leads. You can see them here pretty clearly. Those are from the module. They connect into the microinverter. And then there's like this wiring harness that's running here. Kind of hard to see, but just kind of imagine a wiring harness. That's the AC wiring that we saw before that was in the green. Here's kind of another view on a roof before they put the modules down. We have some racking. That's laid down first, and then the installer is putting the microinverter on and making the electrical connections. It's pretty simple to do. It's not real complicated. I mean, the hard part is being on a roof. I mean, he's got fall safety hazards, you know, slipping off a roof and dropping your tools, that can be pretty treacherous. Plus, it's tough working on a roof. You know, it's steep and it's hot. Yeah. It must not be too hot of a climate there because he's got shorts on. If it's really hot, you want to put on long pants because anything you touch is going to be hot. Oh, this is a video on DC arcs. So let me see if I can run this. It's got a YouTube link. Oops, that didn't work, not like I expected. I was telling you about, I mentioned real quickly that DC can be dangerous. Let's find out why. DC can be dangerous because it sustains arcs very easily. And once an arc starts, it's tough to get it to stop. But with AC, it's a little bit, oh, maybe that's a bad link. Oh, maybe this is it.
Welcome to a presentation of PV fire safety. What you are about to see is a demonstration of the risk of arc faults inherent within two inverter technologies. In this demonstration, we have a meter, a scope, and a gap to simulate a wiring fault. The experiment will begin with no gap. The rods will then be slowly pulled apart, simulating an arc gap from a wiring fault, such as a loose connection. In both cases, inverters are exporting power from the solar modules to the utility grid. The first case simulates a string inverter scenario.
Remember, you've got 600 volts of DC there.
Kilowatts to the grid. As we establish an arc by simulating a wiring fault, the arc gets hotter and hotter. Temperatures can reach up to 4,200 degrees centigrade. This is hot enough to melt tungsten. The second case illustrates a microinverter scenario. The microinverter is exporting 170 watts to the grid. As you can see from this scenario, only the smallest of arcs is visible.
Did you see it?
And for a very brief moment.
It's just a little
The
spark.
nature of a microinverter is that the arc is self-extinguishing. Here is another look at the two scenarios, side by side. We hope this helps illustrate the differences in arc fault risk in the two inverter technologies.
So, and one of the things, you know, with AC, I'll turn that off before it starts. With AC power, you oscillate through a sine wave. So, say you start at 0, you go negative, you go through 0 again, you go positive, you go back through 0. So you're always going through 0 crossings, and that helps extinguish the arc because you can't get an arc at 0 volts. But with DC, the voltage stays constant, and that's why that arc continues to propagate like that, and it just continues on and on and on. So they're inherently more dangerous. They present a higher risk of fire in a situation like that. So that's one of the another advantage of microinverters. You have a much lower voltage system. And then there's some other technical reasons inside the inverter that kind of help out with this too. And maybe after the meeting, if you want to write something up on the board, we can do that and show you. But it's one of the inherent advantages is that it's much, much safer. Okay, let's see.
One other question.
Yeah.
The AC output of each microinverter, are they all in phase, or you force them to be in phase?
Yeah, they have to be in phase. You know, the grid that we're hooked up to, the utility, you know, it's got nuclear power plants and Hoover Dam behind it, and it's very, very powerful. And it has a lot of inertia. I mean, you can't change the frequency very easily because you've got all these all these generators that are keeping the frequency constant. In fact, the generators are actually locked together through GPS, time sources and so forth to keep it exactly at 60 hertz, as close to it as possible. There are faults in the system that can change frequency. Imagine, one of the, a good example is in Hawaii. I got my Hawaiian shirt on today too, because I know I was going to talk about Hawaii. Actually, I wear Hawaiian shirts a lot, so just so you get the memo, tomorrow is Hawaiian Shirt Friday, by the way. Hawaii is a good example. It's an island, of course. They have to generate power. They don't have a big population there, so they don't have any nuclear power plants. They don't have any. There's some geothermal. They can use wind. They can do PV. But historically, power's been generated through diesel generators. So they have a motor running, burning diesel, spinning a generator, and it's spinning at 60 hertz, and it's pushing out power onto their grid, and they have multiple generators that are doing that, and everything's synced up. But if they lose a generator, what happens? Now there's more load on this first generator. Well, imagine a car. It's just like it's a car engine. It's an engine, like your car engine. When you hit a hill, what happens? If you got your foot on the accelerator, you go up that hill, you slow down because it's more of a load on your engine. That's exactly what happens with the generators in Hawaii. When they lose some generation due to many reasons, circuit breaker opens, the telephone pole gets knocked down, whatever, you put more load on the remaining generator, and its frequency will go down until they can apply more fuel to speed it back up. So you'll get a dip in frequency as a chance to come back to normal. So that's what's happening there. The frequency can change, but for the most part, it's constant. The same thing if, and you have, and also if load disappears for some reason, what would happen, it's like going downhill for these generators. If load disappears, you have less load on the engine, and the frequency will rise. So the inverters have to keep up with all that. They have to keep in step. They have to keep locked to the frequency. Frequency is not constant. It's pretty constant in California, the U.S. It's pretty rock solid. But in places like Hawaii, where the frequency can vary quite a bit, even during the day, every day. So the inverters have to keep synchronized. How do they do that? Well, they have a phase lock loop inside, and they're looking at the zero crossings of the sine wave, and they're counting pulses. They have a digital counter that's running on a clock. I think it's around a megahertz. I'm not exactly certain what the frequency is. But it's counting how many pulses are between each zero crossing, and then it's using that for an internal phase lock loop to generate our control signals to know when to switch and stuff, when the zero crossings are. We need to know the zero crossings for a lot of reasons, and when we get into some of the schematic, I'll show you why. But that's also another way we can stay in sync with the grid. And each inverter is autonomous on how it does that. And each one has got a phase lock loop and is looking at that. Because if it gets out of sync, it can't win. This is a 300-watt inverter, let's say, and it's trying to arm wrestle with Hoover Dam. It's not going to win. It's going to get knocked off the grid. The grid will pump more current than it can handle into it, and that'll be the end of that poor little inverter. Won't stand a chance. But it's important to be in phase. Also, when you're connecting, let's say that a cloud came over and it was so much that the inverter couldn't export power anymore for some reason, and then it's now sunny again, and now it has to start up. It has to find the zero crossings again. We have to do that, lock up the phase lock loop, and then inject power in the right phase. Or the desired phase. Because with, I mentioned phase because if current and voltage are out of phase, then you have a phase angle between the two You can have current leading the voltage or lagging the voltage, and there you get reactive power. And reactive power is useful for the grid because it can help regulate the grid voltage. So anyways, we can get into, maybe that's another talk. We can talk about advanced grid functions. So I want to talk about storage. Enphase makes storage. This is kind of our product line in a nutshell. We have generation. These are the microinverters up on the roof. That's kind of our main deal. We have energy management systems. Imagine that. So energy management systems could be like thermostats, could be hot water heater control, timers on air conditioners, those kinds of things. Then we have energy storage, which are batteries, if you will. And then control, some way of kind of synchronizing all the activity, the power flow back and forth from the generation to the storage, from the storage back to the house, what gets exported to the grid. There's a lot of control. It has to manage all that. So let's take a look at historical applications for storage. Why did we use? Why do we need this storage stuff? Well, if you're off grid, that's a good place to have it. Here you got your PV modules on the roof, and you can store the energy there in the batteries, and then at night you can run your lights and keep your refrigerator going. So if you're not connected to the grid, that's a traditional way. This is where storage comes from. Historically, this is where the industry has grown. Especially up in Northern California, out in the woods, where there wasn't a lot of grid out there. A lot of the hippies, people like me, they would build these systems with solar modules and lead-acid batteries, and that's how they were able to stay out there. So that's a traditional application. Another one is backup. This is like when storms come along, you want to be able to have energy saved, and then when the power goes out, when the grid goes out, this is if you are grid connected, then you could then use your storage for powering your lights and your refrigerator and so forth. Or when the fires are coming through and all the power goes out. So those are traditional. The new use cases are, one of them is self-consumption. So some of the utilities are requiring that you not export power to the grid. The grid can be a nice storage system too. With what's called net energy metering, you can, your PV is running, you're generating power. If you have load in your house, it'll use that first. It'll take that PV generated power and drive your load. But if you have excess power, where's it going to go? It'll push it back out to the grid. Effectively, what that does is runs your meter backwards. And then, if you had, so the net on your meter is going down negative. So then at night, when the load goes up and the PV goes down, you can pull back some of that power. That's what's called net energy metering. But some areas the utilities are disallowing that. One area is Hawaii. They don't allow exporting power to the grid. Australia is another place. A country does not allow exporting power to the grid. So you've got this excess power. What do you do with it? Well, you could curtail your PV output. Remember on the IV curve, you could run down the curve. You could curtail its output. Or you could store it into batteries. And as soon as once your batteries are topped off, and if you still have excess energy, then you could curtail back down. But at least you stored it, and then you can use that energy later on in the day when the PV can't put out as much. So this is kind of an example here on a graph that shows you how you can store energy during the day and then use it at night. So we have this blue kind of curve, looks like the Golden Gate Bridge. This is your demand curve. So here you are at night, 12 o'clock at night, everyone's sleeping, you just have some phantom loads, your clocks on your microwave oven are on and your clock radio is plugged in. But then people wake up, they start turning on the coffee pot, hair dryers are on, those kinds of things. So your demand goes up in the morning, Then people are going to school, going to work, demand during the day goes down. And then, of course, when you come home at night, again, things are being cooked, maybe the washer and dryer is running, those kinds of things. So you use more energy at night, and then it kind of repeats itself the next day. This orange curve is the PV output. So here in the morning, the sun is coming up, it doesn't put out much, but as the sun rises, you get more and more PV output here. And then this is where the PV output exceeds the demand. And so that comes down here. This is now stored into the battery. So you're meeting all your demand, but you store the excess energy. And here I've stored, during the day, I've stored this much energy down here. Then at night, I can replay that out and reduce my demand at night. So that's the basic concept of how the storage system works. Another economic case is called peak demand reduction. This is kind of an interesting case. So when you look at your power bill, you get charged for every kilowatt hour that you use. You have a baseline rate. Then if you go above that baseline rate, you pay more per kilowatt hour. And then, I don't know, PG&E around here has got like 4 or 5 tiers. So as you use more and more power, it costs you more to use. But for a lot of commercial buildings and industries, and probably even this campus, there's what's called peak demand rate. So the kilowatts aren't based, or the price isn't based on just kilowatt hours used. Their cost is based on the peak kilowatt hours used. So here we have this curve here, of bumpy curve. Look, there's this huge peak of demand right here. So now my rate is based on this number, not my average, but this peak demand, this peak power. This is real problematic for like agriculture. For instance, a farmer who's got cows and he wants to milk them in the morning. In the morning he turns on all his pumps and he's milking his cows. He's got a lot of peak demand in the morning. And that's what his rate for the entire day is going to be based on, that peak. So this is where storage can really help, because now I can discharge my batteries during that time, lowering my peak to say this new level here. And then I can, charge the rest of the time. I can get charge off the grid the rest of the time. So this is peak demand reduction. So we're reducing the peak demand, reducing the total cost of your energy for the day. And economically, doing this, the economic return payback on something like this really comes out quick. Your payback comes out pretty quick. So anyways, Enphase makes what we call the AC battery, and you say, whoa, the batteries are DC, why are you calling that an AC battery? Well, that's because we have the battery, the charge controller, the battery management unit, and the inverter all in one box. So there's a battery in there, and there's an inverter. So the connection to your house or building is through AC. So that's why we call it an AC battery, AC plus battery. And it's pretty simple, it's easy, it's modular, safe. This unit, it's a little bit smaller than a microwave oven, a small microwave oven. It's, it's about like this, not too deep, a little smaller than a microwave. It has 1.2 kilowatt hours of energy, and it has an inverter which is 270 watts. Well, one of these is not enough for a house. It's not enough. You probably need 3 or 4 or 6 to really meet your demands. Yes, sir?
So what do? Do you first rectify the AC that you're getting off of the panels, and then you feed the battery, and then from the battery again you use the inverter?
Yeah, well, this doesn't need PV modules at all, because it's hooked up to AC. If we go back to this peak demand thing, you don't necessarily need PV modules. You could be working, this could be hooked up straight to the grid, and it's just there to lower peak demand. But if you were to take a look at the power path from the module, yes, it's DC out of the module. It goes through power conversion through AC, goes onto your panel board, your circuit breakers, and then you have another branch circuit that has your batteries on it, and that is also, then it has to take battery voltage, or takes that AC and converts it to DC, a regular power supply. charges the battery, and then it has to return that energy back to the grid. So then it's converting it back from DC to AC. So you have, in this system, there is what we call round-trip efficiency. So you have an efficiency when you charge the battery, which is, for our system, is about 97%. And then you have the efficiency going back out, which again is about 97%. And then the battery there's battery efficiency too, because batteries heat up when you charge them. We all know that from our cell phones. You charge up your cell phone, what happens? The thing gets hot. Well, that's lost energy. That's inefficient. It's the energy you put in X watts in, and you're getting X minus that heat that's actually going into the battery, because part of that energy was lost. So there's an efficiency for charging the battery. Our battery efficiency, I don't know, it's like 96%, I think. Overall, the whole thing, you multiply 97, 97, 96, I think the numbers are. I remember the overall efficiency is like 89% in and out. It is what it is. I mean, this is physics. You can't really change it. You're gonna have some losses here. It's not a perfect ideal world, but everyone's got the same problem. You know, we're not any worse than anyone else. We're pretty good. Our efficiency numbers are pretty darn good. Okay, 96% round trip efficiency for battery. That's a little bit misleading. That's just the battery. Okay, the inverter is 97 in, 97 out. So if I don't know, someone want to multiply out those three numbers, see what they get. It uses this LFP chemistry, lithium iron phosphate. So it's similar to lithium-ion batteries, but different from you know, what you have in a car. Those are lithium-ion batteries, or nickel metal, or I'm sorry, magnesium cobalt chemistry. And for a car, you want certain characteristics. What do I want in a car? Well, when my battery goes low, I want to be able to charge it quick. Yeah, I want to charge it quick. I don't want to wait all day to get it charged. I want to go into my charge station, I want to plug it in, get my level 2 charger on, and I want to get going. I want that to charge fast. Now, I'm in my car. What do I want it to do? Well, I like to go fast. So I want to be able to step on that accelerator. I want to be able to discharge that battery really, really fast, because I want performance. I want my Tesla 3 to really be zooming. So that's great for a car, but for a house, that's not really what you want. You've got all day to charge it up, so you don't need to charge it in 15 minutes. And you don't want to discharge it real fast either. You want to discharge it slower, because you want it to last longer in time. So other chemistries are better. This LFP is better for that kind of slower charge, slower discharge. It also helps with efficiency. If you're trying to charge a battery fast, it's going to heat up. You're going to have more losses. You're going to be pumping more current. Ohmic losses of the conductors, you know, trying to change the chemistry around inside the battery, it's going to heat up. If you charge it slower and discharge it slower, you'll have higher round-trip efficiency, because it'll run cooler. So that's some of the advantages. The other advantage of LFP is the safety aspect. I'm sure you've seen the YouTubes out there. You could look at them of Tesla cars that are catching on fire out in the road because they got into an accident, and batteries are flying out, and this thing is burning forever. And it's because there's a lot of stored energy in there. I mean, Tesla batteries like 70 kilowatt hours of storage. I mean, it's got to go someplace. Well, it's discharging quickly, violently. And then, of course, the chemistry itself is catching on fire and causing gases and so forth. The LFP technology is just a much slower rate of discharge. So you know, I've seen pictures of you know, the kind of the lithium, cobalt chemistries when they've failed, and it's very violent. But you get, you know, flames shooting everywhere, smoke, ball of fire. But when you puncture or squish an LFP battery, it looks more like it still burns, but it burns more like a candle than an explosion. So it's kind of a safer chemistry. It's better chemistry for the house. We think that's the best choice.
Yeah, Mark, the 10-year warranty is really great. I wish I had that in my computer, for my computer, and also iPhone, right?
Yeah.
Yeah, that's
10-year
good.
warranty, and it's like 80% of charge. 7,300 cycles. That's 2 cycles per day is kind of the average there. So you would have, you could actually, if we go back, think back at the curve with the demand, where we had demand in the morning, demand at night. You could actually discharge the battery during the morning, that morning peak. You can then charge it during the day and discharge it again at night. And then you could charge again from the grid and again use it during the morning. You know, they have what's time of use rates that the utility has, and what that does is it incentivizes you to use energy at night and de-incentivizes you to use it during the day. So you have a higher rate during the day, but a lower rate at night, which is kind of nice if you have an electric vehicle, because you get to charge it at night at a lower rate. So anyway, so that's what the 7,300 cycles is all about, is that it allows for 2 discharge and charge cycles during the day. So you could use your PV to do one of the cycles and then use your lower time of use rate at night to charge it for the second. Let's see. Oh, it's simple to install. There's a bracket that goes on the wall. There's some AC wiring that goes between each one, and then you hang the battery onto the bracket. Now we get to see Nick Soleil.
How many of you know Nick Soleil was here? He graduated last year.
He graduated last year. He works at Enphase. He's been there
He's
for...
one of the best engineers there.
Absolutely. Because SSU is turning out some great people.
Thank you.
Okay, let's see.
Roughly what do these cost? AC
It's like $1,000 each, but we're working to get the price down some more. Whoops, I got an extra colon in there.
How does that compare to other batteries in the market?
We're a little expensive right now, but that's why we need some smart people to help us get that cost down. And we have some plans to do that. So this is going to be a video of an installation. We're getting a 4.8 kilowatt system. That's 4 of those, and we're going to install it by one person in 1 hour and 40 minutes. So it's a long video. Oh, we sped it up. So there's Nick Soleil. He graduated last year. We gave him a couple cups of espresso, and right now he's kind of measuring the conduits, cutting them to the right length. He's putting in these little junction boxes, getting kind of the layout. And there he's putting on the mounting brackets. This is 4 of them, so he's got 2. The mounting hardware is right at 16-inch centers, which bolt right to the studs of your typical North America housing construction. So there you go. We also have a bracket for European installations that have a different spacing. So there we go. We got the 4 brackets. The conduits are there. He's pulling wire through the conduits and just kind of trimming them off. Pulling the wires. Now he's putting on the terminations for each one. He's connected it into the load center there, the circuit breakers. He's got a voltmeter out there, check the voltages, everything looks good. Kind of buttoning things up. And he puts the batteries on one, next one, putting in the safety covers underneath it. Now they're powered on. He's got a cellular phone which then talks with the system, and he's able to commission, what we call commissioning. So he's able to set up the proper profiles and connections for that system. So it's commissioned, it's hooked up to the grid. So that was pretty cool. So I have some resources here. These are some links and stuff. So reference material. There's some really good stuff here from the National Renewable Energy Laboratory. So the federal government has scientific labs. You know, you've heard of like Berkeley Labs or, geez, what are some of the other ones? I'm drawing a blank. Sandia, some of the others. So there's a National Renewable Energy Laboratory. It's in Boulder, Colorado. It's a really beautiful place. They're doing a lot of good work, some really cool stuff. So go on their webpage and scour around there. There's some awesome stuff. Solar Pro magazine is another one. This is a professional magazine. It's a good one. I like it. Another one is Home Power. Home Power is more kind of off-grid stuff, kind of more like grassroots. Solar Pro is, you know, gets more into commercial utility scale, that kind of stuff. So both those magazines are good. Solar ABCs, unfortunately this website's kind of going into a little bit of disrepair. But anyways, I get involved in quite a bit of stuff there. This is a lot of the permitting and standard stuff. ABCs, forget what that stands for. But it's a good stuff. There's a lot of good information in there about grounding and degradation of PV modules and these kinds of things. So I think that's it for me. Oh, here's some more. Wikipedia, of course, it's got a lot of really cool stuff. I got some of the information there about solar cells. EC&M Magazine's another good one. And then, of course, go to the Enphase Energy website. We got a lot of neat stuff there, too. So there's a lot of good white papers, how-tos, demonstrations, you know, all kinds of neat stuff there. That's it. Any other questions? Yeah, question in the back.
Yes. Recently, PG&E has come up with this idea that they're going to charge customers more between the hours of 4 and 9 p.m. So your batteries are going to work beautifully for that purpose.
That's right. It incentivizes storage systems. Yeah. That's where their peak demand during the day is usually in the evening hours, because a lot of industry is still running, and then people are coming home and turning on their electrical devices. So that's where the highest peaks are, in those hours.
Yeah. I heard that PG&E also is going to disallow getting the energy, receiving the energy. Is it true or not?
Yeah, they have what's called that net energy metering, but that program is actually going away in time. So they want to get away from net energy metering. They don't want to provide that service to people with PV systems and whatnot.
Right.
So that again incentivizes storage, and that's why storage is. There's a lot of good movement out there for that industry, and that's why you'll see more and more of it as time goes on.
In other words, they're going to allow receiving energy, or they're going to disallow it. I mean, I thought that they are disallowing it.
I'm sorry?
Are they disallowing receiving
They will.
energy?
They will, yeah. We call that export.
Yeah, the export.
Zero export. Yeah, eventually. Today, when you connect in a system, you connect into an interconnection agreement called NEM, Net Energy Metering, and that allows you then to export energy to the grid. But you don't get to export it at the same price that it costs you to buy it. So when you export, you're only getting like 6 cents a kilowatt hour. But when you buy it, it costs you 17 cents a kilowatt hour. So they've changed some of those rules, and then eventually NEM is going to go away completely, and you'll have zero export policies. Like I said, in Hawaii, that's generally the case. They have two programs called Customer Self-Supply, which is no export, and Customer Grid Supply, where you are supplying energy back to the grid for some credit. But they're changing that. They're eliminating that. The amount of installations allowed under the CGS plan is going down quite a bit, and they're also changing their rates where if you export during the day, you get no credit. But if you export, I think it's from 9 to 4, you can export to the grid, but you get zero credit. You don't get it paid for it at all. But if you export to the grid from 4 till the next morning, you get a measly chunk of money, much less than what it costs you to buy it. So they say they purchase your energy at the wholesale rate, but you buy it at the retail rate. Yeah.
What's the mean lifetime of the microinverters? And what fails? Is it electrolytic capacitors?
I'm running out of batteries here. Electrolytics don't fail much in our system, believe it or not. It is a common problem for inverters to have electrolytics fail. But you have to look at how the circuit is designed. And we don't design, when we have electrolytics in there, we don't try to run a lot of ripple current through there. We keep the ripple current low, because ripple current is, of course, what is ripple current, first of all? Imagine a capacitor's got some stored DC voltage and there's some energy stored in there, but then you're pulling or pushing energy in, so you're generating a ripple on top of that DC waveform. So you have that ripple current in and out of the capacitor is what's called ripple current. And the capacitor itself has some finite impedance. There's the inductive elements, ESR, and ESL, the source resistance and inductance. And as you're pushing current in and out, you're generating heat, and that's what wears out the capacitors. But if you design your system to have a low ripple current, then you're going to put less stress on the capacitor. The other thing you can do for a capacitor is that you can take a look at its temperature rating. They have capacitors that are rated at 105 degrees C or 130 degrees C. Well, we use a capacitor that has a very high temperature rating, and if it's rated at 105 degrees C, well, it's sitting up on a rooftop that never gets that hot, so we're not stressing it. And traditionally in string inverters, there's and then the amount of capacitance we put in is not that great. But in string inverters, you have very high voltages. Number one, you've got 600 volts. Sometimes you have to take capacitors and stack them in series to get them to give you the full voltage that you need. And then you got to put them in parallel to give you the amount of capacitance that you need. So you have these huge banks of capacitors, and they're pumping a lot of ripple current in and out of the thing. So that's what kind of wears out the capacitor more than anything else. So if you design your circuit such that it doesn't stress the element, then it'll last longer. So that's how we get by with the lifespan of the electrolytics. We don't see a lot of electrolytic failures. I mean, we track very closely what the failures are. Every unit that fails in the field, we bring it in and we take it apart and we do a root cause analysis on every single one. And if you come to see the factory tour, you get to see that, where we do that. We cut open the case, we dig out the potting compound, and they debug it right down and find the root cause. So some of the root causes are maybe we had a bad batch of components, maybe it was solder connection. There are failure mechanisms. And then every generation of product that we sell, we go through an extensive life testing. And life testing, you can accelerate the lifespan of the product by running it up and down in temperature, cycling it on and off, up and down in temperature. There's the whole field of reliability studies that you can follow. I mean, it's a discipline in its own for doing accelerated life and reliability studies. And then we see that we pass. We use mil-spec standards, which are very rigorous, and we see that we pass. So we don't stop there. We keep testing it. We test it till it fails, so that we can figure out what was that weakest link. Then we can take a look at that. Is this something that's that we can fix? Is it a part problem? Is it a manufacturing problem? Is it a design issue? And we feed that back into our design process and try to make appropriate changes. Every generation of product we came out with the M175, the M190, M215, the 250, the S series, now the IQ series, IQ6, now IQ7, 8. Well, I didn't think I used my first thumb, so I guess that's only 7. 7 generations. Every time we've come out with a new generation, we've improved the qualities of it. A lot of our failures actually end up with water ingress, and we've had issues with that in the past. Water ingress is the killer, because with water gets inside, then it corrodes something. and causes it to fail. So M175 was not a very good mechanical case to keep water out. M190, we improved it. M215, 250, we got it even better. Now the IQ series is even better yet. So we have it's a polymeric enclosure. It's plastic. The two pieces are, circuit board is put inside. The two pieces are mated. Then we ultrasonically seal it. We have we fill it up with a potting compound. Potting compound is like kind of like a gelatin, a little firmer than Jell-O, and it fills up all the voids inside. So now there's no place for water to get in. Where's it going to go? It can't get into the parts because something's already taken its place. It displaces water, and that kind of stuff. So we've learned how to do that better and better every generation, and that's how we get the reliability up. And that's why we have a 25-year warranty on our product, too.
Okay, now it is, all right, 5:42. I would like to thank Mark for his excellent, really, we noticed that. Excellent.
I hope you enjoyed it.
Presentation, and I really learned a lot, and I'm sure you did all. So let's just give him. I asked him about the tool for those who are in the EE497. I think he can do it next week. The point is that he has usually from 4 to 5 a meeting, that in fact he's hosting, and we need to move it now from, let's say, 5 to 6 o'clock or so. Is it okay with all of you then? You think that you can make it? I mean, next week.
Next Thursday.
Yeah, it's next Thursday, yeah.
Will we still present?
What?
Do we still have to present next?
Well, we can move your presentation. That's matter. That's okay. I sent an email. I just want to see now, because I need to communicate also with the EE club so that we have some students also from.
We have class at 6.
What? You have a class at 6?
Yeah, we both do.
Okay. So maybe then we need now to move it then now somehow, then, right? So we'll talk about it later. So the pizza is there then, Sharon, right?
Yes.
Oh yeah. So thank you very much again.
Yeah, thank you too.